Problem-solving illustrations for short and medium transmission lines. Let's have illustration 1. So there is a single-phase overhead transmission line delivering 1,100 kilowatts, 33 kilovolts at 0.8 power factor lagging. Okay, so from these given parameters, we can see that these are the receiving end power, voltage, and power factor. Okay. The total resistance and inductive reactance given as 10 and 15 ohms respectively. Determine the sending end voltage, the sending end power factor, and the transmission efficiency. Okay, so since it is not even specified if it's a short or medium transmission line, we are safe to assume that this is a short transmission line, diba? There is no line length given, wala. But in this case, this is not a medium transmission line because, number one, there is no given capacitance or even admittance, diba? So remember, the short transmission line doesn't consider the C's, diba? Yung Y, the admittance. But in this case, diba ang medium should have the Y. Kasi the medium transmission line should have Y whether we will be using nominal pi or nominal t. Okay, so since doesn't have y given, so this is safe. We are safe to assume this is a short transmission line. Okay, so first things first, so get the sending end voltage. Okay, so simply we get the equation for Vs, specific for short transmission line. Okay, which is Vs is equal to Vr plus ZIR. Okay, so one by one, we'll have Vr, which is already given. 33,000 volts, 0 degrees, or 0 degree. Okay, the angle 0 degree. And then the Z is also given, 10 plus J, 15. Now for IR is simply, we have to use the power formula we had in our circuits. AC circuits. So 1,100, that's the real power, and then 33,000 for the voltage, and then 0.8 for the power factor. Okay, so we just have also to get the angle. Okay, so the angle is simply cosine, inverse cosine 0.8. Okay, so we plug in negative, okay, because it says there that the power factor is lagging. Diba? So this is just a bit of review of your circuits 2, AC circuits concepts. Okay, now given all those values, we just have to plug them in. Okay, plug them in the equation Vs is equal to Vr plus ZIR, and then we will get the quantity 33,709.26 0.425 degree volts. Okay, so sending end voltage is simply like that. Okay, next is the sending end power factor. Okay, so in getting the sending end power factor, we might have to draw the phasor diagram. Okay, so first thing, you write the VR. Okay, so VR is our reference. Okay, so pwede namang iba yung reference, but the simplest, okay, phasor diagram, ang reference natin is VR. Okay, and then from there, we plot Vs, which is theta 1 from VR. Okay, so where do we get that? Yung kanina, diba? We have our Vs equal to quantity Vs or magnitude Vs, theta 1 degrees. Okay, next is Is. Okay, we plot the Is, which is also equal to IR because this is short transmission line, and theta 2 from VR. Okay, so having all those, I think the power factor is simply cosine theta S, wherein your theta S is the angle between Vs and Is. Okay, and from the phasor diagram, your theta S will simply be cosine theta 1 plus theta 2. So therefore, your power factor at the sending end is 0.7955 lagging. Okay, so that is how we get the power factor of the sending end. Okay, next, the transmission efficiency is PR over PS times 100. Okay, so I think we have PR, but we don't have PS. However, we can obtain PS, okay, by having this. VSI is power factor of the sending end. Okay, since this is single phase, okay, so wala tayong factor na square root of 3 or 3, no, in our PS. So, we have VS, we have IS, meron na tayong power factor. Okay, so, plugging them all here, we will have PS as, efficiency, which is 98.45%. Okay, so I think we will have an illustration wherein we will be using another way of computing the efficiency, no? Okay.